Okay, so picking up from where we left off, um, we've covered. Um, let me move this over here somewhere. Um, Move it over here. We have covered vertical asymptotes and holes, but we haven't covered horizontal asymptotes. So I want to spend some time kind of reviewing that um, to know the behavior of horizontal asymptotes, also called end behavior. So I got a lot of words to go over, but I'm going to go over some vocabulary again. Notebook out. We've already taken these notes before, but always good to have new notes. Those were given on a toolkit. Always good to have notes in one place, like your notebook. So I really recommend you sort of copy the toolkit notes into your notebook. So degree. This is a vocab word we need to know. I'll talk about, well, we will talk about the degree of a function, the degree of an expression. It's just talking about the highest exponent in expression. Okay. So when you write definitions and you're taking notes, my recommendation is you write the word definition, right? Highest exponent in an expression. You might want to you can rewrite that as in some other way too, but always good to put an example. Always good. So, and again, you don't have to use my example. You can use any example you want. If I had x plus x to the fifth plus 5x squared plus x, the degree of this would be 5 because that's the highest exponent. Okay, that's it. That's all degree is. But you do have to know what that word means to understand, or not to understand, but to engage with, I guess, horizontal asymptotes. Okay, so horizontal asymptotes and end behavior. I'm going to cover both of these at the same time when I erase this. I don't use this anymore. Um, so again, I'm just going to use HA because this is horizontal asymptotes, another vocab word. Um, so horizontal asymptotes are visually, if we had vertical asymptotes that went up and down, horizontal asymptotes go side to side like this. They are lines that functions follow when they stretch to infinity or negative infinity. So we talk about end behavior. It's like where, excuse me, where is the function going? Function. Okay. Sorry about that. I'm going to rewrite that. That's atrocious. Function going as x goes to infinity. So we're talking about end behavior or x goes to negative infinity. These are where they're related, right? So horizontal asymptotes show where the output of the function is going as x goes to infinity and negative infinity. So as in this case, if we just had I made up a function, if the function would look like this, function may look like this. It's what the function is trending towards, heading towards, getting closer to as x. So this would be x goes to infinity. This would be x goes to negative infinity. Okay, so that's all a horizontal asymptote is. Um, and to find this, uh, to find this line here, you essentially have to memorize. I wouldn't say you have to memorize it. I think it's more important to understand. Once you understand these rules, you don't necessarily need to memorize them. You'll be able to intuitively find where the horizontal asymptote is. So um, I already went over these rules. They're not rules, they were situations. Um, but once you understand the concept behind it, you don't necessarily need to memorize it. You just understand the concepts will help you just by looking at a rational function, be able to figure it out. So number one is degree. I'm going to use some shorthand because it's very awkward to write on this. Degree of numerator greater than degree of denominator. Okay, so example, x to the fifth over x cubed. That's degree of numerator is greater than degree of denominator. Conceptually, this makes sense because really x to the fifth of x to the third is basically x squared over 1, right? If I'm simplifying this, and that means that the function is going to follow the behavior of the x squared. It's not going to trend towards a specific line, if that makes sense. So as x gets bigger, it follows x squared. It doesn't follow toward a specific line. Okay. Circumstance number two, degree of n numerator less than degree of d denominator, right? So example here is just flip them, x cubed over x to the fifth. Now this, so let me make this clear, this is no HA. In circumstance one, this is no HA. In circumstance two, let's look at the function first, right? So if I were to simplify this, this is the same as 1 over x squared. So what's going to happen to this function as x goes to infinity, right? If x is, or negative infinity, if x is going to infinity here, or x is going to negative infinity, we're going to end up with a very, 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 very big number here, right? And we're going to be doing 1 divided by that. 1 divided by a very, very, very big number is always going to approach 0. So we're going to have an HA at y equals 0. Okay. Degree of numerator less than degree of denominator. Okay, does that make sense? So as the reason that happens is because as when we simplify, we're left with 1 over x squared in this case, or you might be left with 1 over x or 1 over x cubed. And as x gets bigger and bigger and bigger, because we're doing 1 divided by it, it's just going to get closer and closer to 0. And then maybe you'll be asking me, but what about all the other exponents? Like, what about if we go back to my degree definition? Get over that one. I guess over here, like, what if I had these x, like I have x to the fifth, what about that 5x squared, what about that x? Couldn't that stop that from approaching 0? But the thing is, we only care about the degree because the degree is the highest exponent and it basically makes all the other exponents irrelevant. Because when you get to a bigger and bigger, bigger number, this highest degree here dominates, right? Imagine if you have 10 to the fifth versus 10 squared. Then you have 1,000 to the fifth versus 1,000 squared. Essentially, like the highest degree of the expression dominates the expression as the numbers get bigger and bigger and bigger, if that makes sense. I'll go over that more when I'm back in person, but that's why we don't care about, well, that's why we only care about the degree, not the rest of the expression. Okay. And the last situation is where the degree of n equals degree of denominator, right? So for example, 3x squared over 2x squared, right? Both have a degree of 2. And in this case, we will have an HA. So in this case, I guess conceptually speaking, we have 2 evenly matched degrees, right? So if we think about them simplifying, when they cancel, right, what are we left with? They cancel each other out. So what we're left with is 3 over 2, right? So as x gets increasingly big, the only thing separating the numerator and the denominator, right? The only difference really is their coefficients, right? Also vocab word leading coefficient, coefficient at the highest degree, okay? 3 over 2. So that is where our HA happens. HA at y equals 3 over 2 in this case, right? It's basically you just divide the coefficients, you divide these. I would write that down. So again, good to take notes on this again, because this is important stuff. I have a bit more time. I would like to cover like graphing them. So now that we have, so if I go back to my example, where'd it go? I can find it again. Oh, there it is. All right, so in this case, to find the HA, you're going to look at the degree of the numeric order. I can see I'll give you this to just try. What would the horizontal asymptote of this be? Okay, the horizontal asymptote of this is just going to be 3. HA would be at y equals 3 because the degrees are the same, right? D equals 2, D equals 2. And so it'd be 3 over 1, right? 3 here. And then remember, like we kind of have an invisible 1 because there's nothing in front of the x squared. So it's 3 over 1. So that's y equals 3. So in this function, we could now graph it because we have all the information. I kind of want to show you that just so I'm going to add some of those delta problems just so you get practice. So we have a horizontal asymptote as y equals 3. It's right here. I need a reminder about what the whole, so the whole was negative 2, 1/2, and then 2 was the, so this was the vertical asymptote at 2, and the whole was at negative 2, 1/2, so roughly here. So based on looking at this, I can sketch my graph, right? It's going to trend towards infinity, towards 2 there, and then it's going to trend up to infinity here, and then it's going to be going down to infinity here, and then coming back up, hitting the hole, and then going towards 2 as it goes to negative infinity. If you're ever unsure of where your arrows should be, you can always plug in values into your expression. So if I'm like, okay, where should I be at 0? Should I be below the curve or above the curve? Like, what side of the asymptote should I be on? You can plug in 0. So I get 8 on top and negative 4 on bottom, which is just negative 2. So technically at 0, I should be at negative 2. For the sake of this, it's just a sketch, but that's, if you're unsure of where you need to be, you can always plug in values and then you can find them. And once you have like your value, once you know you're in this like section of the asymptote, you know you're not crossing the asymptote, so you can just sketch your graph within that. Okay? All right, thank you.